Dr. Madhu Mutyam is a professor in the Department of Computer Science and Engineering at IIT Madras. His research interests include computer architecture, heterogeneous computing systems, interconnection networks, and secure processor microarchitectures. He is associated with the Programming Languages Architecture and Compiler Education Lab, which is called the PACE Lab at IIT Madras. He's a senior member of ACM and IEEE. So, and let me just add, he's a great teacher. So again, I don't have to tell you, please make the most of this opportunity. So Madhu, it's all over to you.
Yeah, thanks. So yeah, so the next 1.5 hour, so what I'm going to do is I'll explain this instruction level parallelization, and then at the end we'll have a case study. I'll take one Intel processor and then explain whatever we discussed till the time with the real processor. Okay, so I'm sure that so you've already learned the pipeline processing and so on. So that means instruction pipelining and so on in the previous lectures. So now I'm going to look at how to deal with the programs which have the instructions that can be executed in out of order fashion, which is effectively like if you have parallelism at the instruction level, how do we exploit that and then get better performance than a scalar pipeline processors and so on. So that is the main idea of this lecture. So here, when we say instruction level parallelization, so we'll be looking at independent instructions at runtime when the program is being executed, and using the hardware components, we try to identify these independent instructions and schedule them onto the available functional units. Okay, and anyway, so at any point in time, if you have any the concerns or questions, please interrupt me so that I can clarify your doubts. So the main part of the superscalar processors or instruction level parallelization based processors is the dynamic scheduling. So we schedule the instructions at runtime. Of course, the static scheduling is like compiler is going to schedule the instructions and so on. And the dynamic scheduling is at runtime, depending on the instructions which are independent and so on, and depending on the availability of functional units, we'll be scheduling these instructions onto the available hardware units. So if you are going to use just a scalar pipeline where instruction processing happens in order, that means whatever the order given by the original program, the compiler, the compiled code has set of instructions, in the same sequence the instructions are going to be processed one at a time. So we push one instruction into this instruction pipeline processor, and then the next slot, next cycle, another instruction will coming into this particular pipeline processor and so on. And this entire processor is divided into maybe a 5 stage or 10 stage or whatever, and each of these instructions will go to the next stage and so on. So every cycle, and as a result, like if you see in an ideal scenario, a k stage pipeline processor is going to give you a throughput of k times compared to a non-pipeline design. But if you are looking at the instructions per cycle, every cycle you are going to get one instruction coming out of this pipeline processor. But the thing is, like if you want to extract more performance, that means if you want to improve IPC, that is nothing but instructions per cycle, if you want to increase, then the scalar pipeline processor is not of any help. So we need to look for some other alternatives, and one such example is the superscalar processors, where rather than a scalar pipelining, now we are going for a superscalar. In other words, we'll be issuing multiple instructions, we'll identify multiple independent instructions from there, and then we schedule them onto the available functional units, and at the end, we'll be getting multiple instructions processed coming out of this superscalar pipeline processor. So there are disadvantages with the scalar pipeline system, and to handle that, we are proposing this superscalar pipeline processors. And in this dynamic scheduling, so we'll also eliminate it, because there may be dependencies among the instructions, and the dependencies can be a true dependency or false dependency. For example, if I consider two instructions, add R1, R2, R3, where R1 is the destination, R2, R3 are the source operands for add instruction, and then there is a next instruction, multiply R5, R1, R6. So now you can see R1 is a source operand for multiply operation, whereas R1 is destination operand for add instruction. So now multiply is dependent on add instruction. So that type of dependency is called as a true dependency, because the later instruction is trying to consume the value produced by the previous instruction. So in such cases, we cannot do anything unless until the value for R1 is available. We cannot schedule multiply instruction. So we have to keep the multiply instruction waiting until unless R1 value is updated. But that type of thing, anyway, we cannot do anything. But there are other type of scenarios where, for example, if you consider add R1, R2, R3 and sub R1, R5, R6. Now, if you see here in both these two instructions, both instructions, R1 is actually the destination operand. And now they are actually, if you look at the destination operand, they are same. So as a result, there is a dependency, but there is no flow of information. And that is actually called as an output dependency. And similarly, you also have, so these are basically, one is previous cases like previous instruction is producing the value and the later instruction is consuming. That is called as a true dependency. And output dependency is nothing but both instructions have the same destination operands, but there is no flow of information. That is called as an output dependency. And there is also another thing called as an anti-dependency. The example is, let us say, add R1, R2, R3, where R2, R3 are the source operands, and the next instruction multiply R2, R5, R6. Now, if you see, R2 is the source operand in add instruction, and R2 is the destination operand in multiply. There is no flow of information because multiply is coming anyway later to add. But if you just look at the same operand is there in two places, and this is actually called as an anti-dependency. Among these three type of dependencies across instructions, the false dependencies are nothing but the output dependency and anti-dependency. And these things actually you can eliminate easily by renaming these registers, and that is called as a register renaming. And we are going to discuss later how register renaming can be done. And once we do this register renaming, we can eliminate all kinds of these false dependencies. And once we break this false dependency, automatically these instructions are now independent, and we can schedule them onto the available function units. So because objective is try to find independent instructions, large in number, ready instructions, and schedule them onto available function units. That's the basic idea of any superscalar processor. And we rearrange this dynamic scheduling also rearranges the instructions at runtime to reduce the stalls while maintaining the data flow and the exception behavior. Data flow is like, for example, the first case I've given, right? A true dependency, where obviously this later instruction has to come later compared to the previous instruction because it is waiting for the value produced by the previous instruction. So as long as if the data flow constraints are there, so we are just following those things. And similarly, any exception behaviors and so on, we are following. But for example, if there is a load instruction and which is trying to read the value from a cache, and that may not be available immediately, and it may be taking some time and so on. So in such cases, we can actually delay our subsequent instructions unless the value is available. And so we can, some of these instructions in the program, we can rearrange to fill the slots in the pipelines. Because typically what happens is if you're not going to rearrange, there may be some pipeline bubbles, and that is going to increase your overall execution time. But dynamic scheduling ensures that such type of bubbles can be minimized. The main advantage with the dynamic scheduling is it doesn't matter.
Yeah. Madhu, there is a Madhu, can I just interrupt? Are you writing anything on the slides?
No, no.
Oh no. Okay, fine. Some students were thinking that you are.
No. Yeah. But whether my slide movement is there or.
Yeah. Slide movement is perfect. Yeah, it's all good.
Yeah. So I'm not writing anything on. I just because it's too simple example, and so I just orally mentioned.
Sure. Perfect. Yeah.
But the other things, there are some examples, and I have that in the slide itself. Yeah.
Sure. Thanks, answer.
Yeah. So the advantage with this dynamic scheduling is it allows code compiled for one microarchitecture to run efficiently on different microarchitecture. What does that mean? For example, if you see Core i7 processor, Core i5 processor, or Core i3, all these follow the same ISA instruction set architecture, but the microarchitecture is different, right? So you can compile the code maybe on a Core i3 processor, but the same compiled code, you can actually execute on Core i7 processor. And there may be a difference in their cache hierarchy. There may be a difference in execution latencies of different functional units and so on, but it doesn't matter because this dynamic scheduling ensures that all these variations can be taken care. How? Because it is going to schedule an instruction onto a functional unit only when the operands are available. Let us say when it is compiled on Core i3 processor, and so now at compile time, we don't know whether it is going to take 2 cycle latency for an add instruction or 3 cycle latency, and it doesn't matter. But when we are actually executing this compiled code on a processor, now at that time, when it is trying to read the data from a register file, for example, it may be taking 3 cycles in Core i5, and it may be taking 5 cycles in Core i7. I'm just giving an example, right? But now if I'm going to execute this on Core i5 processor, operands will be read only after 5 cycles, and then only the instruction is ready, and then it is going to be scheduled onto the function unit. And similarly, if it is scheduled on Core i7 processor, it may be taking 5 cycles or 10 cycles, depending on the characteristics of this function unit in that particular processor and so on. So as a result, I don't worry about what is the microarchitecture and so on. As long as my compiled code can run on a system. How do we say it can run? As long as the different microarchitectures follow the same ISA, then you don't have to worry about any other things. You just compile the code on one system, and then you can peacefully execute on any other systems and so on. And any variations in these access latencies or whatever will be handled by this dynamic scheduling. And so as a result, as a user or a programmer, you are free from all these headaches and so on. And also, it handles the dependencies that may be unknown at compile time. A simple case is, let us say I have something like if x greater than 5, a condition is there. And at compile time, I don't know whether this condition is going to take place or not take place and so on. And the x value may be known only at the runtime and so on, depending on some other value computations and so on. But those things can be handled here. And similarly, the other thing is like, for example, when you have a load instruction, you don't know whether the load value is going to be available from L1 cache or L2 cache or L3 or main memory. All these things are unknown at compile time, but these things can be efficiently handled at a runtime. That is what even the last point allows the processor to tolerate unpredictable delays. The delay can be because the value is not available in L1 cache, then you have to spend another 5-6 cycles to get the data from L2. If the value is not then L2, then maybe you have to spend 20 cycles to get the data from L3. If not, maybe hundreds of cycles, 200 to 250 cycles to get the data from main memory and so on. All these things can be handled by dynamic scheduling. So once you have a dynamic scheduling support in your processor, then you are free from all these headaches, and then you can freely execute your program efficiently, and which is ultimately is going to give you a better performance and so on. But to support this dynamic scheduling in the processor, what are the things required? For example, I mentioned the second point, register renaming. So we have to see how the register renaming is handled, and how to identify dependent instructions, and how to select independent instructions and schedule them onto functional units. And if a functional unit is busy executing some instruction, what is that we can do with the next instruction? Where do we keep the next instruction? All those things will be handled in the Superscaler processor, and that is what I'm going to explain in the next coming slides. So
Hello.
Yeah.
I have a question that so I came across this like a few days ago that LLVM contains, let's say, a scheduling model of x86. I'm not I don't understand if the scheduling depends on the microarchitecture, then why would they have it? Like the compiler wouldn't be compiling code according to that then, right?
No, your question is like LLVM is handling the scheduling of instructions.
So LLVM, it has a whole model of how a CPU would work, like how an instruction would go through its pipelines and all. Like it has a full blown kind of let's see, you can kind of say call it a cheap simulator, let's say. So I was wondering, as you said here, that instructions we are compiling for ISA, right? Not for the microarchitecture as such.
Yes.
So I was curious why they would need to implement it all in their compiler anyways. If you have any idea, of course.
No. So what you are saying is like why microarchitecture related things are implemented in LLVM. That's what your question, or?
Yes.
I'm not sure, because like microarchitecture is, because it can be varied in different generations of processors and so on. And I'm not sure about this. Maybe the latest LLVMs have that support, but yeah. So because I don't have much information about that, I cannot comment on it. Okay, but generally the comparative things are like they just look at the ISA rather than the microarchitecture. Because even if you do that, let us say if you want to tomorrow, if you want to execute that on something else, then you have to recompile, right? Because if your microarchitecture changed, then what is that you can do? And also again, like I don't know how much information the LLVM can carry from the microarchitecture point of view. Because some of the things, for example, the delays, because we don't know where the data is going to be there. Roughly you can have, for example, once you know the underlying mission, then you can know what is the latencies, function access latency or execution latency of different function units. That's it. You cannot know anything more than that. Okay. So yeah, maybe you can check with some the professors who handles or who do research in compilers and so on. Okay.
All right. Thank you.
So if you see any of the latest processors, and of course we have these days multi-core processors, but within that single core, internally the organization will be something like this, right? This is a superscalar organization. So where we can fetch multiple instructions. In a scalar pipeline processor, we fetch one instruction at a time. But in a superscalar, we fetch multiple instructions, and these multiple instructions are going to be decoded simultaneously, and then they will be dispatched. And these dispatched instructions, depending on the type of the instruction, because after decoding, we know what type of instruction it is, and depending on the type of the instruction, we'll be sending these to different reservation stations. A reservation station is nothing but a buffer where we are going to keep these instructions unless until the function unit is available and the operands are ready. Once the function unit is available and the operands are ready, then this instruction is ready to be issued onto the functional unit so that function unit execute this instruction. And after the instructions are executed, they will be written to a reorder buffer, and from there we'll be taking the instruction one at a time or collection of instructions. Of course, there the program order is followed, and we'll be completing those things. And finally, we'll be writing the instructions onto architectural register. Destination values will be written onto architectural registers. But if you see here, fetch, decode, dispatch, all these things are happening according to the program order. And the execution happens in an out of order fashion. And again, the commit and the return happens in the in order. So the whole idea is, let us say you have multiple functional units with you. Then why can't you make use of all these functional units? That means hardware replication is there, multiple extra components are given, multiple adders, multiplier units, divide unit, and all these things are there. Now you just try to identify whether you have available set of instructions that will keep these functional units busy. And once we are scheduling these instructions onto the function units, now all these function units are executing in parallel. So effectively, you are now getting the parallelization there. In other words, your execution time of one instruction is overlapped with the execution time of the other instruction and so on. In a given amount of time, multiple instructions can be executed. And so that advantage we are going to get with the superscaler. And once we execute these instructions, then we'll be completing in the normal order, writing to the architectural registers according to the program order. Right? So all we need is, we need to identify independent instructions. And that is what we are going to do in the reservation station. If you see in the reservation station, the instructions are sitting. There we'll see if any, let us say, later instruction is actually ready with its operands and the function is available than the previous instruction. Then we can just straight away execute that instruction. But of course, when we want to commit this, we have to wait for the previous instruction to commit. So the commit happens in the program order, but the execution happens in out of order. That is where we are going to actually gain the performance improvement. So identify independent instructions, schedule them onto the functional units, and get more performance. Yeah, someone has a question?
Yes. So it seems like in previous lecture, Govind Rajan sir explained out of order execution. So there seems like there's a bit of thin line between superscalar organization and out of order execution. So can you put some light on it?
No. Superscalar processors actually implement out of order execution. What are the things covered in the previous lecture, by the way?
This true dependent superscalar, sorry, out of order execution and basic computer architecture was covered, including cache management and other things.
Right. But in out of order execution, what are the things discussed? How this
Uh,
out of order
yes,
happen?
reordered buffer was discussed. Reservation station was discussed, but not much in depth. They mentioned that this will be discussed in subsequent lecture.
Okay, but any superscalar processor, there are three important components. Okay, so one is because we have to do instruction execution in out of order fashion. That is the main thing. Okay, and to do that, what we are going to do is, because once the instructions are executed in out of order fashion, but we need to know the actual order, program order. So that is where we are going to have this reorder buffer. So we make an entry in the reorder buffer and then schedule the instructions in an out of order fashion to the functional units. And then at the time of committing, so we again come back to the reorder buffer, and then because the reorder buffer is working like a the first in first out type of thing, so queue type of design, and that is going to ensure the ordering and so on. But so superscalar processor means automatically out of order execution has to be there.
Okay. Kind of these implements the idea of.
Yes. And also because another thing is the superscalar, when I say it's effectively multiple instructions can be fetched, decoded, issued, executed, and so on, compared to a scalar pipeline. Okay, where it's just a single instruction at any point of time. Right? Is that fine?
Yes, sure. Thank you.
So when we fetch multiple instructions, maybe typically if you consider aggressive superscalar processor, you can have a 4-wide superscalar or 8-wide superscalar. In each cycle, multiple instructions are going to be fetched, and parallelly they will be decoded, because you'll have multiple decode units and you decode them, and then you dispatch them onto the reservation station. Of course, you can directly dispatch them onto functional unit, but if you do that, if the functional unit is busy, then that will have a pressure, back pressure will be there. And so as a result, so to delink the functional units with this dispatch, what we are going to do is we put in the middle, there is a buffer, which is called as a reservation station. So we dispatch onto the reservation station, and the instruction is going to wait in the reservation station unless until satisfying those conditions where the functional unit is available and the operands are ready. So we route the decoding instruction to appropriate functional units, but before that, we will be placing them into the decoding instructions into the reservation station. And anyway, I know that after decoding, whether instruction is an ALU instruction or a load instruction or a control instruction and so on, and depending on that, we'll be moving these instructions onto the appropriate reservation stations. Of course, there are different type of design, centralized reservation station versus distributed reservation station and so on. We'll see that in the next slide. This is the organization of a reservation station. Whether this reservation station organization is also discussed in the previous lecture?
No, it wasn't discussed.
Right. Okay. So this is a reservation station, which is like a buffer, and where every time when the dispatch instruction is there, we are going to identify one free slot, and we are going to put the instruction into that slot. And each slot, if you see, it consists of these things, because typically, so we have like 2 source operands will be there in an instruction. So operand 1 and operand 2. And we also have a busy bit for each entry. And each operand also has a valid bit. Why are we requiring this? Because when we are dispatching an instruction, operands might not be ready, because the previous instruction is not yet completed its execution to produce a value. So in such cases, what we are going to do is we are going to provide the tag into the operand field. If the value is available, we will be supplying the value. If the value is not available, we will be supplying the tag. We will discuss how the tag will be distributed, stored here and so on. And depending on that, we are going to put the valid bit. So if the original value is stored, then valid bit is equal to 1. Otherwise, valid bit is 0. And similarly for the other operand also. Now, if both operands are ready, that means both valid bits are 1, then we are going to make the ready bit to 1. And once ready bit is set, that instruction is now ready with the operands. Now it is ready to be scheduled onto the functional unit. That is the idea. And now operands may be ready, but the functional unit is not ready. Let us say you have one multiplier and multiplier is already busy with another multiply operation. Now, when you have a next multiply instruction, even though operands are ready because a multiplier is not available, so the instruction is just sitting in the reservation station unless and until the multiplier is available. So once multiplier is available, then we'll be checking, we'll be coming to this reservation station associated with the multiplier, and then we'll see which are all the instructions that are ready to be scheduled. And now we'll pick one of those ready instructions and schedule them onto the function unit. And this is where again we can consider, maybe if you want a simple solution, we just consider the one which came earlier, or the age-based priority we can consider, or there may be some techniques like, okay, if I schedule this instruction because there are many dependent instructions waiting for this instruction to be executed, in such case I can consider a later multiply instruction and so on. So different policies are proposed here in the literature, and that are going to select one of the ready instruction, and that ready instruction is going to be now scheduled onto the function unit. So here also, whether in the previous lecture this operand forwarding is discussed.
Operand forwarding in a sense, data forwarding.
Yeah, so when there is an instruction which is, for example, there is a previous instruction, produce the value, and that value required by a subsequent instructions.
Yeah, true dependence. Yes, it was discussed.
Yeah, so this is again like to support this operand forwarding, we have this forwarding slots here. That means, let us say I have two instruction, add instruction and multiply instruction, and multiply is waiting for the add to be producing the value. Now, once add produces the value, normally what happens is when add produces the value or any functional unit produces the value, that value needs to be returned to the destination register. And now the subsequent instructions are going to read from the registers. But if you do that, then effectively it is taking more time, because writing to a register file and reading from the register file, each register file, typically if you consider modern processors, register file access may take multiple cycles. And that is going to degrade the performance. Rather, what you can do is when add is producing the value, this value will be returned to the register file, but parallelly it will be forwarded to all the instructions which are sitting in different reservation stations. And it will be checked with the tag, because when the function unit produces a value, it supplies, okay, this is the value and this is the tag associated with this particular thing. If any instruction waiting for this tag data, then they can take it. So that is what we are going to have a forwarding path, and in that forwarding path we will be supplying this data from the function unit. And now for that, to support that, we have this forwarding slots here. So there are dispatch slots and the forwarding slot. Dispatch slot is like when we dispatch instruction, we'll be direct writing into it. And the forward slot is effectively when previous instruction is finished its execution, the data will be forwarded on the forward path, a bus connected to that function unit, and that will be returned to the appropriate locations wherever there is a match in the tag. And now once we have tag match, then the data is going to be stored, and then we are going to put the valid bit to 1. And once both operands are ready, then this instruction is set to be ready to be executed.
Sorry to interrupt, but this forwarding slots, right? So, I mean, the figure in the figure, the one in the bottom is one entry, right?
Yes.
So this forwarding slot, is it being occupied? Let's say instruction I, and instruction I gives a value that is required by, say, I plus 3. So will I plus 3 instructions forwarding slots get the value produced by I, or will I slot get the value that has been forwarded?
No. See, when instruction is dispatched, when instruction is scheduled onto the functional unit, this entry is removed from this reservation station. So you have only I plus 3 instruction in the reservation station, and which is waiting for the value produced by instruction I, right?
Okay. So
as a result, I value will be forwarded to this reservation station, and if I plus 3 is requiring that data, then it can take it.
Okay, so I plus 3's entry will hold this value, right?
Right.
Yeah. Okay. Good.
Right. So it's a simple case, like for example, add R1, R2, R3. R1 is the produced value by add, and multiply R5, R1, R6. Now multiply requires one of the operands from the add instruction. So the moment add produces the value for R1, that will be forwarded to multiply instruction. Multiply instruction is sitting in one of the entries here. And now in the R1's tag place, the data is going to be coming in. That is the idea.
Yeah, understood. Thanks.
Sir, it also suggests that forwarding slots will be more, let's say, tougher to implement in a superscaler architecture than in a scalar one, because here the reservation station is the overhead for the hardware designer to implement.
Right. So this is basically what is happening is like you have, in order to forward, you need to have a bus connecting to, for example, in a scalar processors, what is happening is like you have only one instruction at every stage of the pipeline, right? Pipeline register, you have only one instruction you are holding. And now when you forward, then you are forwarding to that single entry buffer, which is a pipeline register. But here, instead of the single entry buffer, you'll have multiple entry buffers, and you can have multiple such reservation stations. A common bus connecting to all these reservation stations, and that will be forwarded.
Okay.
So there's a common bus on which you place the data, and this bus is connected to all these reservation stations, and they will be reading the data, whatever is placed on the bus. Okay. Of course, from the design point of view, obviously, for compared to a scalar processor, superscalar processor is complex in design because you need to handle all these things and so on. Right? So the reservation station decouples the decoding and the instruction execution, as I mentioned previously, because instruction, when you decode and dispatch, operands may not be ready or the function may not be ready. So then it is effectively holding the instructions till that time, till that satisfies these two conditions. And the main tasks of reservation stations are dispatching, waiting, and issuing. That means from the dispatch stage, we dispatch instructions into the reservation station. How do we dispatch? We first identify a free location in the reservation station. Let us say you have 4 entry reservation station. Now you want to dispatch one instruction into the reservation station. All we have to see is whether is there any entry which is free. How do we know? There is a busy bit associated with each entry. If busy bit is 0, indicating that that entry is a free entry. If none of the busy bits are 0, that means everything is full, then in such cases, we cannot dispatch any instruction into the reservation station. We have to stop there. Unless until there is a free entry, you cannot push new instruction into the reservation station. Once we dispatch, now instruction is sitting there. How long it sits there? As long as operands are not ready or functionality is not ready, it is just waiting in the reservation station. Once operands are ready, now ready bit is set. And if the functionality is free, now we have issue logic, which is going to go through all these instructions in the reservation station, and it picks one of the ready instructions, and that will be scheduled onto the functional unit. And it checks the structural and read after write hazards. Can anyone tell me how this is happening? With the reservation station, we handle the structural hazards, we handle the read after write hazards. I'm sure, I think these read after write, write after write, all these hazards are discussed in the pipeline design, the earlier lecture. How do we handle the structural hazards in reservation stations, using reservation stations? What do we mean by structural hazard, by the way?
Structural hazard is when you try to use the same functional unit at the same
lack of resources, right?
Yeah,
lack
I mean, yeah, in this context, it would be using the same functional unit.
Right. So if you have 2 multiply instructions and we have only 1 multiplier, and multiplier is busy with 1 instruction, then we are not going to schedule the next instruction because that instruction is sitting in the reservation station. So we handle the structural hazard. What about read after write hazards?
That's the true dependence, right?
True dependency, because read after write means in the previous example, R1 in the multiply instruction is actually waiting for the value to be produced by add instruction. Add is going to write to R1 and multiply is going to read from R1. So now there is a true dependency, read after write. Multiply wants to read from the register only after add writes to R1. And such type of things can be handled because when multiply instruction is issued into the reservation station, and operand is not available unless until add completes its execution or finishes its execution. Till that time, we have only the tag of R1 and the valid bit is 0. So that also handles here. So effectively, true hazards, a true dependency part is properly taken care by reservation station. And it also handles the structure hazards. Now, true dependency part is taken care. Now we have to see the false dependency. False dependency is handled by reservation register renaming. Already I mentioned in the previous slide. Now we'll discuss that in detail about that. So this reservation station, again, different processors implement this in a different way. There's no uniform design or whatever. And some people will think that maybe it's a good idea to consider centralized reservation station. Okay. And some may think that no, it's better you just have reservation station for each type of operations. Maybe you have one reservation station for add operations, one for multiply operations, one for control instructions, and depending on the things and so on, right? So you can have those things, and this reservation station is tied to the corresponding functional units. So that is one thought of design. But anyway, so both have their own advantages and disadvantages. If you consider centralized reservation station, basically your dispatch buffer itself is acting like a reservation station. And now from the decoded instructions in the dispatch, we'll be dumping all these instructions into the centralized reservation station. And from there, we'll be selecting the instructions and schedule them onto the functional units. That means all functional units are now trying to read from the centralized reservation station. Obviously, when multiple functional units trying to read the data from a centralized reservation station, you need to have more number of ports for this buffer. And if you have more number of ports, it is going to take more area and it consumes more power. Because the lines, your interconnect lines are now, actually the wires which are connecting your buffer to the functional unit where you are supplying the data and so on. So you need to now have large number of wires because multiple ports are there. If it is a single port, then it's fine. If you have 2 ports, total number of wires will be now double. And everything now you have to connect to each of the bit positions and so on. So that's the reason why it is complex when you have more number of ports. And that is also adding up to your overall access latency and power consumption. But Intel actually prefers this centralized reservation station. And the other one is, if you see PowerPC architectures, they consider distributed reservation station. From the dispatch buffer, they take the instructions and move that onto separate reservation stations, one for adder, one for floating point unit, multiply, load store, and different things and so on. But now if you see, if you have a distributed reservation stations, you'll have a lesser number of entries in each of the reservation station. Of course, let us assume that total number of entries for the reservation station is same in both the cases. And in the centralized, we may have 8 entry reservation station. In the distributor, we have 4 reservation stations, each is having 2 entry. Now, those who prefer centralized reservation station may say that, okay, what happens if I have more number of integer ALU operations? Then I can make use of this 8 entries efficiently. And whereas if it is a distributed, you have only 2 entries for integer ALU operations. And so you cannot schedule multiple instructions. You cannot move multiple integer ALU instructions into a 2 entry buffer. That is what their idea. But the distributed reservation station people say like, okay, but if I have this simplified reservation stations and each is having a single port, it is not going to consume more power and it is taking less amount of latency and so on. So again, there is no uniform design, but they have their own advantages and disadvantages. But in summary, generally, if you have a centralized one, entries can be efficiently utilized. In the distributed one, you'll have a single ported reservation station, and that is actually beneficial in terms of reducing the access latency and the power.
So I have a question.
Yeah,
so,
go ahead.
There's one more hazard, right? I mean, let's say a branch instruction is getting executed.
Right.
In some functional unit.
Control hazards. Yeah.
Yes, control hazard. So let's say if branch prediction was wrong and we executed something. So there are already instruction in this
in the
reservation system, right?
Right.
So what will
What do we do with
happen?
that? What do we do
Yes,
with
yes. And let's say the branch is, let's say, a far branch, and all the instruction are, let's say, useless for this, for
Yes.
completion the execution.
Yes.
Then what
What
will
will
happen
be done?
with?
Right. So basically, so this is basically you are issuing the instructions based on some speculation, right? You predicted the branch is going to take place because the moment there is a control instruction, none of these modern processors are just waiting for the branch to be resolved. So they just take the help of a branch predictor. And branch predictor says that, okay, previously I encountered this type of branch and previously it has taken. Now also it is predicted to be taken. Now we just take that branch and then we just execute instruction from the taken path. But that when we predicted, because it's not sure, but it's only a speculation. And now when we are executing instruction in a speculative fashion, then we are going to set a bit in a reorder buffer that I'm going to discuss in the next slide. There is a bit set, and that bit is set because this instruction is executed speculatively. Once at the end, the branch is resolved. Now, if the prediction is indeed correct, then we just come to this reorder buffer and reset that bit. So that from the system point of view, nothing happened and it is executing in the normal fashion. But if the prediction is wrong, in such case, then what we do is when we come to the ROB, we just flush all those instructions. Wherever the entry which is set to 1, we just discard those. So though there may be some computation happen, but none of these things are written to the architectural registers. So the state of the system is not changed, and then nothing is going to happen. That is what typically we do. Got it?
Okay, it is kind of, let's say, just like pipeline cleaning, and similar
Yes.
thing will happen in reservation station.
Right. It's a pipeline flush.
Okay.
So we speculatively execute something and we flush the pipeline if there is the wrong speculation happens. And to support that, we have another important component in the Superscaler process, that is reorder buffer. One is the reservation station, the other one is the reorder buffer, third one is the register renaming. These three are important to come up with this out of order execution of instructions and exploiting instructional parallelization, and those are the main components of any superscalar processor. Right. So this is a reorder buffer. As I said, in the architecture of superscalar processor, some portions are, some pipeline stages are in order, execution is out of order, and the complete and the retire, those are again in order. So to handle this, then we have a reorder buffer. It contains all the in-flight instructions. In-flight instructions are nothing but the instructions which are dispatched and instructions which are not yet committed. That means any instruction which is there in the pipeline after dispatch till the end of the execution, those will be called as an in-flight instruction. And when we dispatch, what are we doing? We are making an entry in the reservation station, right? Because if you see the previously, so here I mentioned, so the allocate unit, where whenever we are dispatching an instruction, we are just identifying a free entry in the reservation station and allocating an entry. So basically, an in-flight instruction is the one which is there in the reservation station, or it is there in executing stage where function unit is currently executing, or it finished its execution, but it is just waiting in a rename register, and finally it will be written to the architectural register and so on. So all those instructions are called as in-flight instructions. So these in-flight instructions are nothing but the instructions which are there in the reservation station, are instructions currently being executed on functional units, are instructions which are finished their execution. That means, let us say add instruction, add R1, R2, R3. Add is finished its execution, but add value is not written to architectural register R1. Maybe it is written to a rename register and so on. Why? Because we have to write to R1 only when this instruction comes to the head of the ROB. Only when it comes to its particular slot of finishing, till the time the instruction value will be there in a rename register. So all those instructions are called as in-flight instructions. And at the time of committing the instructions, we have to check whether the instruction finished its execution and whether the instruction is non-speculatively executed. Any non-speculative instructions are going to be committed. So that is where I mentioned previously, if it is a branch instruction we speculatively executed, but if the speculation is not resolved, then we are not going to commit this particular value into an architectural register. When I say commit, we have to write the value into an architectural register. Till that time, we have to just hold that value somewhere. And to implement this, typically it will be something like this. Reorder buffer is a queue type of design where you can see there are multiple fields in each entry. And the first bit is busy bit, which is actually saying like every time when we want to dispatch an instruction to a reservation station, we also make an entry into reorder buffer. And to make an entry into reorder buffer, we come to this reorder buffer and we'll see, is there any entry with a busy bit 0? If the busy bit is 0, then we'll be taking that. There is a pointer, tail pointer, and that location we are going to store the new instruction. And once we store an entry, store an instruction into a reorder buffer, now if the instruction is now ready with the operands and the functionality is available, then we'll be issuing this instruction onto the function unit. Then we'll set the issue bit. And now once we issue the instruction onto the function unit and the function unit starts executing, after maybe a couple of cycles, instruction finishes its execution. That means add operation is done. Then we'll come to this particular thing and then we'll set finished bit to 1. And we also have instruction address. But now, because we are, of course, on the next slide, we will be discussing register renaming. But every time when we are dispatching instructions, and so we are going to rename the destination registers, and the rename register value is also going to be stored here. And if it is speculatively executed based on some prediction, then we are going to set the speculative bit to 1. And if the speculation is wrong, or for some reason we want to flush some of these instructions which are executed earlier, we'll come to this valid bit and we reset it. So at the time of committing, we just look at this entry and see whether the valid bit is 1 or not. If the valid bit is 1, then only we are going to commit that instruction. In other words, we'll be writing the value into architectural register. This is what is going to happen in the reorder buffer. Now you can see, I don't care whether I execute instructions in an out of order fashion or whatever. Ultimately, I'll be committing the instructions only in the in order, because reorder buffer is clearly saying you have to just execute in this order, because always the committing happens only from the head pointer, and head is always pointing to the first instruction. And even if the third instruction is ready, the first 2 instructions are not ready, then you cannot commit the third instruction unless until the first 2 instructions are done with their commit operation. So this is what is going to happen here. This is the main component, key component of any superscalar processor, and which handles all these things: speculation, out of order execution, and even forwarding part. So everything is actually, basically this is the main component through which we are executing instructions in out of order fashion. If this is not there, the out of order execution part is not going to be successful, because if you out of order, if you reorder the instructions, there is no way you can come back to the original order. But whereas ROB is maintaining the original order, because every time when we are dispatching instruction to a reservation station, we are making an entry, and dispatching to an instruction reservation station happens in the program order. So the same order is maintained in the reorder buffer. So that is the main idea behind this. Right. So the last 2 stages of our superscalar architecture is the completion and the retire. Is there any difference between instruction completion and instruction retire? What do we do in the instruction completion and what do we do in instruction retire? So completion is nothing but to finish the execution and update the mission state. Okay. So for example, if you have an add instruction is there, which finished its execution, and now we will be writing the data into the architectural register. If you do that, then it's said to be complete. And retire is updating the memory, because when we have this processor handles the ALU instructions as well as the memory instructions, control instructions, and so on. And ALU instructions are basically all these arithmetic logic operations where function unit finishes execution, and then you will be writing to the destination register. In the case of a store, what are we doing? We have the value in the instruction, and that value we have to store it into a particular memory location. The address is also specified in that instruction. We have to go to that location and then write the data into the memory, and that happens in the retire stage. A store may complete by writing to the store buffer, but it retires only when the data is written to the memory. What is this? Can anyone say what is the store buffer and why do we require the store buffer? Any idea why we are considering the store buffer?
It could be that because memory is slow, so processor can just write to a buffer and continue executing another task and do not retire the instruction.
Right. So basically what happens is, like, if you are asking the instruction to write to the cache, let us say if it's a store instruction, and if you ask the store instruction to write to the cache or memory or whatever, it may take multiple cycles. Generally what happens is there will not be any instruction, there will not be any instruction dependent on the store instruction. But whereas there may be many instructions dependent on the load instruction. A load is loading the value from the cache or the memory, and a store is writing the data to the cache or a memory, right? So now what we want to do is we always want to give preference for loads over stores. So it means we want to keep this cache or memory as much free as possible, so that if there is any subsequent load instruction coming in, they can actually use that cache or memory. And that is the idea we consider. And because the stores are given less preference over stores, the loads, so what we do is we write these values into a separate buffer. Of course, a buffer access is taking less latency compared to the cache or the memory access and so on. And because of that, we'll be writing the stores into a store buffer in the completion stage. But from this store buffer, we'll be writing to the memory or the cache when the cache or memory is available. So that can be done at a later point in time. Otherwise, if the store buffer is full, then we have no other option. We have to write it. Till that time, we can keep accumulating the stores into the store buffer. By the way, is it going to create any problem? If there is a store instruction which is sitting in the store buffer and there is a load instruction coming later, and indeed that load requires the value whatever we have written previously, is it going to create any problem?
If there are multiple stores to the same location, that might be a problem.
No, multiple. No, that you can actually store buffer. You can have this merging.
Right. Okay.
Yeah, that's. But even if you have multiple, then so you can always take the first one, the latest one, to supply. But the first of all, what happens is, if you are updating the values, if you are writing the values into a store buffer, and if there is a later load comes up, and if the load is not checking in the store buffer and directly going to the cache, then it may read a stale copy. So to handle that situation, every time if there is a load instruction coming in, then we have to first search in this store buffer and see whether any entry in the store buffer can supply the data to a load. If it is so, then we'll forward. Otherwise, we can just go ahead to the cache or a memory and so on. So those things, of course, when we come to the load store operation processing, we'll discuss those things in detail. But right now, you just consider that there is a store buffer where we'll be storing these values and at the completion stage. And when an instruction is retired, then we take the value from this store buffer and write it to the actual cache or a memory. And again, when there is an interrupt occurs, let us say we are executing a program and there is an interrupt occurs, right? So now what we have to do is we stop fetching the new instructions and finish the execution of all the in-flight instructions, right? So what are all the in-flight instructions? So I said previously, all the instructions with this busy bit 1 and the valid bit 1, right? So all those are basically the in-flight instructions, and you execute these things and then don't fetch any more instructions and so on, then service interrupt service routine, and then come back to the normal execution of this program. So the main idea here is, because already some of these instructions are there in the pipeline and have done partially their computations and so on, and why can't we make use of that? That's the basic idea. So we just complete the execution of those in-flight instructions and write it to the architectural register, and then go ahead with the interrupt service routine and come back to the normal program again. And when there is an exception happens, the result of the computation may no longer be valid. In such cases, So what we are going to do is like our processors can support precise exceptions, where basically what we do is we checkpoint the state of the mission. State of the mission is nothing but all the architectural register contents and so on, right? So we'll be checkpointing that just prior to the execution of the exception instruction, an instruction which is causing an exception, divide by 0 or something, right? And then we resume the execution by restoring the checkpointed state. So every time, like when there is a exception happens at instruction I, the prior to that we just save the state of the mission and then handle this exception, and then again start executing the checkpoint, the exception created point onwards, because we have to re-execute the instruction and then by loading the state whatever we saved earlier. And this also again handled by your ROB, reorder buffer, because we know at what time it happened. Because if you again go back to this reorder buffer, you can see here, let us say at the third instruction we had this exception. So all the instructions just before that particular exception creating instruction, we just complete the execution and save the state and then handle the exception and then come back to this third instruction and again executing remaining things. So the difference between exception and the interrupt is, interrupt means all the in-flight instructions are going to be executed and then handle the exception, the interrupt service rotate. But whereas in the exceptions, because when there is an exception, you have to handle that and then re-execute the instruction. So any instruction coming after that makes no sense. So we are just stopping there and we just save the state just before the exception creating instruction, that is checkpointed, and then we restart from that particular point after handling the exception. So this also can be handled if you have reorder buffer. Basically, it has like reorder buffer has lots of advantages, and all the current processors are implementing this reorder buffers, because Superscaler is the minimum thing that is there in any of the processors these days and so on. Right. So I said previously, register renaming is another key component in any Superscaler processor. But we'll see, why do we require register renaming? So for that, we have to first focus on what all the scenarios where registers are reused. Why can't we give infinite number of registers? If you have a program, you can consider infinite number of registers and so on. But in reality, your number of registers, architectural registers, are limited, and that is determined by your ISA, instruction set architecture. There may be a 16 registers or something, right? So those are the limited number of registers. You have to make use of that for your entire program, right? So that is where, like, and also, for example, if you have a loop, there is a, in a high level construct, you have a for loop for I equal to 0, I less than 100, I plus plus, and you have some add instruction in it. Now, typically what happens is, when you are executing this loop at runtime, and different iterations of this for loop will be there in different stages of the pipelining. Now, they may be using the same register, but in different scenarios and so on. So the same register is appearing in different places and so on. That's, in other words, same register is reused. And in fact, in compilers, one of the optimization stages like register allocation part. Initially, it assumes infinite number of registers, and then they will be finally mapped to available architectural registers and so on. And when we are executing that at runtime, because the same register can be there because of this multiple iterations of this loop body is going to be appearing when we are executing, and because of that, they may be there in different pipeline stages and so on. So static reuse occurs due to the compiler optimizations which will be done. And so code initially assumes unlimited number of registers, and finally it will map to a limited number of registers that is specific to ISA. But at runtime, because of this loop body, when it is executed, then maybe multiple iterations are co-located in the entire pipeline. And because of that, the same register which is there in this loop body, when it is going for the next iteration and so on, the same register is appearing and so on. So as a result, the same register is occurring in multiple places in your entire in-flight instructions and so on. And if you are not taking care of that, then there will be, you can, by looking at the registers, you will see that, okay, there is a dependency, and then you want to stop subsequent instructions to execute and so on. So that will degrade the overall performance. So we need to eliminate such unnecessary dependencies, and then we can just treat them as an independent instructions and then schedule them. Only true dependencies need to be taken care, and false dependencies can be simply eliminated by using register renaming concept. So register reuse induces the name dependency. Name dependency is nothing but output dependency and anti-dependency. These are also called as the false dependency, because the same register is actually the same register is appearing multiple places and so on. Because of that, there is a dependency. Actually, the flow of information may not be there in that. So how do we enforce these name dependencies? One simple solution is, if there is a name dependency, don't execute the subsequent instruction and wait for the previous instruction to complete. But that is actually a crude solution, which degrades the performance significantly. So this is what the option one: stall all dependent instructions until the leading instruction has finished its accessing the dependent instruction register. But that is actually not a good idea, because most of the cases you can clearly see there's no flow of information, and then you can simply break the dependency. Option two is a register rename. You rename the register. That means, let us say if two instructions are using R1 as their operand, one of the operands. Now in one place I just put R1, the other place I'll put R2, for example. Now these two are working on two different registers. One is R1 and one is R2. There is no dependency. So that is the logic we are going to apply in register rename. So we dynamically assign different names to multiple writings of an architectural register. So once we are assigning a different names, now there is no name dependency. So all these instructions are now independent, and they can be scheduled onto the functional units and so on. So for that, what we are going to do is, even though our architecture supports a fixed number of architectural registers, and all these architectural registers are there in a file that is called as a ARF. Architectural register file is nothing but collection of architectural registers. In addition to this, a superscalar processor also has another register file which is called as a rename register file. That means there will be temporary registers, and that can be used for renaming these architectural registers. And typically you can have rename registers up to like some 60-70 registers will be there, and they can be used so that you can have more number of in-flight instructions into this pipeline. Typically, if you see any of these Intel processors and so on, you will have around 100 to 120 in-flight instructions in different stages of the pipeline. When you have a 16-stage or 17-stage pipeline, you can have large number of in-flight instructions and so on. That is possible because you have large number of rename registers, and you can use that to rename the architectural registers. And now, how do we map this architectural register with rename register file? This is what is the idea. So there is an architectural register file which consists of data and the busy bit. Of course, now when we are mapping this with RRF rename register file, which also has a data and valid bits in each entry. Now there is a tag, which is a map table mapping an entry in the RRF with an entry in the ARF. Basically, I take one ARF register, and now I'm renaming that ARF register with one rename register in RRF. And whatever I'm mapping, the corresponding tag, I'm going to put it in the tag field. And using that, I'm just going to see if there is a read request for a register R1. And if R1 is mapped, renamed with something else, by looking at this map table, I'll get the actual register which is renamed with for this particular R1, and I'll try to read the data from this rename register and so on. This is what is going to happen every time when an instruction is going to be dispatched onto the reservation station. We'll be looking at all these things. And now we'll see what are the operations that are happening inside this register renaming part, because you can see when some instruction wants to read an operand, how do we know whether we have to read the value from the RRF or ARF? So that means there should be some mechanism or a procedure that should be followed. So we'll see that what is the procedure to be followed when we want to read an operand. And similarly, when we want to rename, what is the procedure to be followed? All these things we'll discuss in the next couple of slides. So register renaming tasks are three. One is a destination allocate. Every time when we want to rename, we are just focusing on only the destination register for renaming. That's it. We are not touching the source operands. If I have add R1, R2, R3, R1 is the destination operand, and now this particular one only we are renaming. And next, when we have an instruction to be scheduled onto the function unit, we want to read the values from the registers, source registers. So that is what we are going to do, the source read. And similarly, when the value is, let us say, add instruction is issued to a function unit, and it takes the values from R2 and R3, we perform the source read, R2, R3 values are read, and we give it to an adder, adder performed its operation. Where are we going to write the data? Let us say R1 is renamed with a T1. Where are we going to write the value, add value, whether to R1 or to T1? When a function unit adder finishes its execution, in which location we are going to write the data? R1 or T1?
It should be R1, right?
Yeah, but this is because I said instruction finishes execution, not completed. Okay, so when I say instruction finish, it may be because I may be executing instruction out of order fashion, right? There may be many prior instructions which are not yet committed. How can I write directly to R1 now? If I write to R1, let us say any of the previous instructions creates any exception or whatever, I have to roll back, right? But if I already written value into R1 architectural register, then your checkpointed state is wrong, right? If there is an exception or something happens, you have to roll back to the previous state, right? So that's the reason why when you finish the execution of an instruction, you first write it to only rename register. That means in this particular case, we'll write to T1 only, where T1 is a rename register for R1. But when are we writing to R1 from T1? When this particular instruction comes to the head of the ROB, and this instruction is now to be committed, at that time we'll take the value from T1 and write it to R1. Because once it comes to the head of the ROB and instruction is correct, everything is valid and so on, then we'll be now about to commit. When we are about to commit, we'll be actually doing the commit stage, we'll be writing the data from the rename register to an architectural list. After that, the state will be retained. That is the basic idea. So the register update happens in two stages. When the instruction finishes, we'll be updating only the rename register. When the instruction commits, we are writing or we are updating the architectural register. So these three are the tasks that will be done by register renaming logic. And this is, the entire thing is captured in this particular thing. So you can see here from the function unit, when the value is produced by a function unit, we'll be forwarding that data to RRF, update an instruction at finish, and ARF is updated at the instruction completion. And whenever we want to read the data of source operands, we first come to RRF, we first come to ARF, and then we'll see whether ARF can supply the data. If not, then we'll just go to RRF. If RRF is not also going to supply the data, then we'll be taking the tag associated with that. So each of these three stages I'll be explaining in the next 3 slides. First one is destination allocate. So let us say, I just again consider example, add R1, R2, R3. R1 is the destination register. Now what I'm going to do is I'll come to this ARF and go to this R1 entry. And now what I'm going to do is I'll be taking, so one of the free entries in the RRF, and that value will be mapped with R1. So for that, what I'm going to do is when I go to RRF, I'll just try to see a field, an entry with the busy bit 0. If the busy bit is 0, indicating that that particular entry is free right now, and that can be used as a rename register for this R1. And take that register and set that busy bit 1 now, because we have taken already, and now we are mapping that to R1. So we put the busy bit 1 so that any subsequent instruction comes, then this entry is not available, or this rename register is not available. And now what we are going to do, we'll set this RRF valid bit to 0, because this is not actually having the correct value, because it is going to be updated and so on. So that's the reason why we put valid bit to 0. And then update the map table. When we come to this ARF with this map table entry, we'll put the rename register entry tag here. And then we set the busy bit here, ARF busy bit 1, indicating that this R1, if any instruction later comes for R1, once the busy bit is 1, indicating that this R1 is not going to supply the data to the next instruction, and the next instruction has to read the value from rename register. That is the meaning of this. That is the semantics of this entire thing. When we set the busy bit 1 in the ARF, indicating that this architectural register is renamed with another register in the RRF. Right? This is what we are going to do for each destination register in all the instructions. That is the first step we are going to do. Next, updating the registers. That is when the instruction finishes execution, when the instruction committing, during that time we are going to update the registers. That is what we are going to do now. Once the instruction finishes, we take the value and put it into this RRF. For that, so we have this sequence of steps. So we forward the data from the functional unit to the corresponding entry in the RRF, because that is specified by the tag. And wherever there is a match in the tag entry is matched in the RRF, the corresponding value location, we are going to put the data. And once we put the data, then we are going to set the valid bit to 1, indicating that now the data field in this particular entry is actually holding the correct value. That is what is indicated by valid bit to 1. Now when the instruction completes, that means when it comes to the head of the ROB, now we have to commit it. Then what I'm going to do is I'll take this data field, data value, the value in the data field of RRF entry, and we go to this ARF with the map table entry, okay, and we update in the architectural register with this particular data. And there also we'll be doing something. When we update this architectural register, we set the busy bit to 0, so that if any later instruction comes for this particular value, now busy bit is 0, indicating that the value in the data field of ARF indeed is the correct value, and the later instruction can directly take that value and then go ahead with its execution or whatever. This is what is going to happen during the register update part. So first we saw destination register renaming, second is register update, and the third one is reading the source values, because in my instruction add R1, R2, R3, R2, R3 are the source operands. I have to read the value, whether I'll get from ARF or RRF. That is again will be specified by this particular procedure. Okay, so you can see these muxes and so on. The select lines will say whether the value is coming from the data field of ARF or the data field of RRF or the tag from the RRF, whatever. That is specified by these two muxes. If the busy bit in the ARF is 0, then effectively that instruction already completed its execution and the value is directly available in ARF, and then you can fetch the value directly from ARF itself. If the busy bit, that is what is given in the second mux, you can see the busy bit is given as a select line to the second mux. If it is 0, I'll be taking the value from the data field of ARF. But if the busy bit is 1, then I have to take the second value, which is coming from the other multiplexer, and that has two entries. One is the tag field, other one is the data field from RRF. And one of these two will be selected based on the valid bit of RRF. So if ARF busy bit is 1, that means the content in this data field of ARF is stale. So now what we have to do is we have to access the map table, take the tag and go to the RRF, and from there we have to see whether the valid bit of that particular entry is 1 or 0. If it is 1, indicating that the instruction finishes execution but not yet committed. So in that case, we will be taking the value from the data field. Okay, but if the valid bit is 0, indicating that this instruction is currently being executed or just waiting for execution unit to be available or whatever, in such cases, we don't have the data and we can just supply only the tag. That is what we are going to do. Basically, what we do is in that particular case, we will be just forwarding the corresponding tag to the instruction, dependent instruction, whatever is looking for this particular thing. So this is what we are going to use in the register renaming. The three important tasks: destination allocation, updating the register, and reading the values from the source registers. And the source register can be either from a ARF or RRF depending on this particular procedure. So these are the three important components register renaming, reorder buffer, and reservation station. All three R's are the main components of any superscalar processor, which supports execution of instruction in out of order fashion, identifying independent instructions, and also it supports speculative executions and so on. Right? You have any questions? I'll just explain these 3 steps of register renaming with a simple example. Let us consider 4 instructions. Is there any dependency here? Just look at this. And the semantics here is, the syntax is, the first operand is the destination operand, the last 2 are the source operands. That means add is working on R2, R3, and the result will be written to R1, and sub is working on R2 and R1, and the result will be written to R3, and similarly mul and div. Now tell me, is there any dependency here? Between add and sub, is there any dependency?
Yes, in add to subtract, there's a dependency between because R1 is getting written and sub.
Right. What type of dependency is that?
It's a true dependence.
Right. And what about R3?
R3, it's a right dependence. I mean, anti-dependence, you can call it.
Anti-dependency, because R3 is actually, there is no flow of information from producer to consumer. And R3 is actually reading in add instruction, and whereas we are writing to R3 in sub instruction. So there is no flow of information. So this is an anti-dependency. Right. And what about add and mul?
There is no, no.
It is a dependency.
Right after right.
Yes.
Right after right. Right.
Wow.
So output dependency. Both are using the same output register. Right. And add and div. There is an R1, but actually div is dependent on multiply. Right? Because multiply is also writing to R1. Now tell me, when div comes, which instruction is going to supply the data, whether mul or add?
Mul.
Right? Because the mul is actually updating the R1 latest, so automatically div should get the value from mul. Right? And there are two dependencies, and also output dependency, anti-dependency. For example, mul and div, there is an R2. Output dependency is there. Anti-dependency is there. Right? And sub and div, is there any dependency?
Yeah, there's a R3 dependency.
R3. Right? Yeah. And similarly, sub and mul also you have R3. There are two dependencies, anti-dependency, output dependency, all these things are there. Now what we do is, so here this particular code R1, R2, R3 are architectural registers. And let us assume that we have 4 rename registers, R4, R5, R6, sorry, R7, there is a typo. So 4 rename registers are there. Now because register renaming, we have to update only the destination registers. So that means R1 in add, similarly R3 in sub, R1 in mul, and R2 in div. These have to be updated with rename registers. This is what is the logic. First, we have 4 rename registers. Now, when add comes up, we have to update the destination register, that is R1. So we take the first free rename register. Let us say R4 is the first free rename register. We take that and then update. So now add becomes add R4, R2, R3. Source operands are same as that of the original one, but the destination one previously R1, now it is R4. Now when sub comes, so sub R3 is a destination register. We'll be renaming that with the next available free rename register, that is R5. But sub is reading the values from R2 and R1, right? But R1 is already renamed with R4. That is what we discussed, the third task in the register renaming, source read, right? So there, because actually sub is trying to read from R1, but R1 is renamed with R4. So now in place of R1 in sub instruction, R4 came. That is what the sub R5, R2, R4. R5 is because of renaming destination register, and R4 is because R1 in the add instruction is already renamed, and we take that. When the third instruction mul comes, which is R1, R2, R3, again R1 is renamed with the next available free register, that is R6, and R2 we have not done anything, so we keep R2 as it is. But R3 is the one of the source registers for mul, but R3 is already renamed in the sub instruction with R5, So I'll be taking R5 here. So mul becomes mul R5, R2, R5. Now div, last instruction, R2 is now renamed with R7, and R1 is one of the source operands for div. But R1 is recently updated with R6 by mul. So I'll be taking that recently updated one. So R6 came in R1 place in the div. And R3 is already renamed with R5. So now R5. Now if you see this, the second table, add sub mul div, do you find any false dependency in any of these instructions? Is there any false dependency? That means output dependency. Output dependency, you can clearly see no two registers in the destination position of all these 4 instructions are having the same value. So there is no output dependency. And anti-dependency, read from the first instruction and write in the second instruction. Is there any such anti-dependency? Yes or no?
I think multiply and divide has
multiply and divide. What is happening?
R6 is getting written and later R6 is getting.
That is like a true dependency, right?
Oh yes, sorry, it's a true dependency.
Yeah, that is even with add and sub also you can see R4.
R4.
There is a true dependency. So all true dependencies will be there, but false dependency is eliminated.
False are yes. These were the premises because true will remain and false and other things will go.
So basically, register renaming eliminates all false dependencies. And we already discussed previously, reservation station handles the structural hazard and read after write hazards. So now as a result, now your entire system is ready with executing any instructions which have dependencies and so on. If there is a true dependency, the instruction is going to wait. And if it is a false dependency, we are eliminating the dependency and then we can treat them as independent instructions and then schedule them onto the functional units. So this is the basic idea, underlying idea of any superscalar processor, whether it is Core i7 processor or i3 or AMD processor or whatever. Internally, individual cores, if you see, they actually implement this superscalar features out of order execution or instruction level parallelization. Okay. So with that, I'm stopping here, and I'll take the remaining things in the next class because we have 2 classes on ILP. And tomorrow, I think at 10 or 10:30, the second slot we'll continue with the ILP process. And there I'll be explaining you how this memory operations are going to be handled. And also we'll see how we'll consider Intel process, one of the processors, and then we'll discuss these points from the Intel processor point of view. Whatever points we discuss, how was implemented in the real processor and so on. Okay. So that is what the tomorrow I'm going to talk about. And tomorrow afternoon, I'll be taking a class on DRAM based memory and also a brief introduction to memory consistency and so on. And if you have any questions, I'll be happy to take them now.
Can you talk about logical registers and architectural registers in all this context? So my question is coming from the confusion due to the fact that I'm not sure whether rename registers are actual registers or if they're just entries in some table that exists somewhere. So
no. So the rename registers are actually, so there are in the processor we have registers defined by actual processor, actual ISA, right? Those are architectural registers. In addition to that, we have some extra registers. These are like hardware registers available inside. And those are called as the rename registers. We will be using that for all these operations.
Right. So
basically, you can have, for example, maybe around 100 plus total registers will be there. And that some are architectural registers, some are rename registers. These are like the real registers only. But from the architecture point of view, ISA point of view, they have no meaning.
Right. So, no. So, okay. I think my confusion would be cleared by if you answer this question. So, if I say there is a register called R1, that R1 is bound to a physical register, right? Or is it variable what this R1 means when it comes to actual hardware?
Right. So, of course, here when I say add R1, R2, R3, right? But this is effectively, if you write a program at the high level language, and then when you compile, and if you see the assembly code of that, right? So that will be associated with your RAX or RBX or something. So this R1, R2, R3 is the symbolic names we have given here, but these are actually corresponding to this architectural register that specified by your, let us say it's a 64-bit architecture. You have 16 registers, each is of 64-bit, and those registers are named as RAX, RBX, RCX, RDX, and so on. So each of these things are mapped to those 16 registers only, that's it. These are the, so when we have this R1, which is, when we give this, we are indicating to the system that, okay, your value is available in your physical register RAX. And then go and read the data from there. That's it.
Right. But so R1 here is you're telling that R1 here is a symbolic name.
Right.
But okay.
No,
So
but maybe I think a better thing will be like you just write a simple piece of code and then compile that. And of course, you can get the assembly code for that. Okay.
Yeah.
With the -s option or something. Then you can clearly see for each of the instructions what will be the corresponding the registers they specify.
Right, exactly. So that's what I'm asking. So when I get assembly, so I mean we don't even have to go from there. Let us say that we're writing assembly.
Yes.
In that case, we will be specifying physical registers, right? So whatever this dynamic scheduling and renaming is happening after that point.
Yes.
But then at the assembly level, I've already spoken about physical registers that need to be used.
Right.
And then we come in and do this dynamic dynamic scheduling, which then again use symbolic registers is what you're saying. Is that right?
No. So you have given this code with this architectural register, whatever. And now, first of all, why are we doing this register renaming? Of these dependencies among the registers.
Right. Yeah.
Right. And because of the dependency, we are not able to schedule these instructions. Now, what we are going to do is, okay, no matter whatever the register you specified physical registers, now what I'm going to do is temporarily I'm just rearranging those things with a mapping of this physical register with some other register and so on.
All right.
Yeah. So when I do that, I'm going to get the advantages and so on. But finally, even though when I do all these things, finally when I'm going to write it, because architecture is, this add says you have to write to only R1 at the end. I'm going to do that. So only thing is the middle portion, whatever I'm doing, that is transparent to you. You don't know what is happening inside, but finally you will be getting the correct result because we are finally writing to the R1 register only.
All right, got it. Understood.
Yeah.
Just one more thing. So after this point where we give assembly, whatever, I mean, so typically a compiler does multiple passes over the code and optimizes it and then does register allocation and all that, right?
Yes.
So is there a similar, so this pipeline can be compared to that, but at a even more lower level, right?
Which pipelining?
I mean, I don't know if pipeline
the dynamic execution part.
Yeah.
Yeah, dynamic execution happens like because the compiler gives only at the static time, right? Once you get the object code, now we'll be taking that, and now at runtime we'll be taking each micro instruction and then scheduling them. During the time we'll be looking at all this. This is like much lower level.
Right. Okay, cool. Understood. Yeah. Thanks.
Right. So, any other questions? Anyway, so if you have any questions, you can just write to me.
Yeah, I think, after this register renaming exercise, I think what we understood was kind of even after register rename, the program semantics are maintained, whether you write in assembly or whether you want to the program semantics are honored. So regardless of whatever it is.
That's the first step you have to see, right? Because you can do whatever you want, but you should not compromise on the correctness.
Yes, yes.
Right? So that will be taken care.
Yeah, that's the ISA promise, right? ISA and architectural state promise, and regardless whatever you do in the microcode.
Yes. Yeah. Okay. So if there are no other questions, then so yeah, we'll meet tomorrow, the second slot, and I'll continue with the remaining portion.
If you could point us to resources that talk about this microarchitectural level.
Yeah. So I suggest, of course, the computer architecture basically, Peterson Hennessy is the standard book.
No, I mean, yeah, that again, that will deal with whatever you have spoken about, but like the implementation of these things.
Oh, so the again, of course, you can get some of these. For example, the implementation of these things is like a real processor implementation part. You're saying?
Yeah, but like also the like, I mean, if you think about computer architecture, you generally deal with algorithms and like deal with, I don't know, like you will look at them at a theoretical level and then talk about what algorithms can be used. So if there is a similar treatment for microarchitecture.
No. So generally, like for example, if you refer to the Lipasti, Shen and Lipasti, there is a book, Modern Processor Architecture. Some title is there, and if you see that there, they have actually talked about each of the things, how they are implemented and so on in detail. They've given. For example, the material I've covered is actually from that. Okay. But again, so the point is like here. So what do you mean by the implementation details? Because we are not going to look at how it is implemented at the transistor level or whatever, right?
Right. So okay, so I mean, implementing all these things, so does it directly go from whatever we're seeing here, like the renaming is what you're talking about, right? So that had to be written in some micro instructions. So where do I look? I mean, where do I read about those micro instructions? Or
oh, okay, right. Yeah,
I mean, those aren't generally things that would be dealt with in a computer architecture book, because that really isn't computer architecture. I think it will go to
right. But the thing is, like, see, basically what is happening is, like, if you just look at in a crude way, a processor consisting of your data path and the control path, right? And the data path is basically all these functional units. It is the functional units and register file, memory, and so on. And the data path is the data, or the control path is nothing but the control unit, which is giving the signals and saying that, okay, in this particular cycle, this particular thing needs to be done and so on. Right? So now if you see a real processor, now you effectively, you have a control word. Let's say if a microprogram control based thing. So you have a control word which is specifying that, okay, in this particular cycle, these components are going to be sending their data and this function is going to process and so on. So that is what basically at the implementation level.
Right. So if you had to go lower than that, then you would be actually looking at, I don't know, VLSI or something.
Yes.
Okay.
So basically what happens is, like, of course, from the processor design point of view, if you see, people will always, if they want to come up with a new idea or whatever, they'll implement that in an architectural simulator. That means there is a program which is mimicking the behavior of the real processor. And there they incorporate all these changes, maybe a cache design or whatever, at the higher level. And now once they get the performance according to their expectations and so on, now they freeze the design. Then they take that to the RTL level, register transistor level, right? Register transfer level, RTL level, and then they synthesize and so on. So that is basically like the VLSI side of it.
Right.
But yeah, but for us, like, typically when we look at from the architectural point of view or the micro architectural point of view, we will be focusing at a bit higher level. We say like multiply. So it is like a multiplier which is going to perform multiply operation. But now if you go one level deep, whether you are going to consider booth multiplier or array multiplier or something, that will be there. And now how do we implement the booth multiplier? Again, that will be based on like basic gates and so on. And further, you divide that, each of the gates divided into transistor level and so on. So those things generally we are not touching upon here.
Okay.
Right? Yeah.
Hi, sir. Since you mentioned this microarchitectural detail, so I was considering a thought. Let's say how to evaluate these things. For example, you mentioned RRF files, right? Number of registers in RRF file. So, what should be a design point for a CPU designer to consider? Let's say we should include a 64, let's say RRF register or RRF file. So,
Yeah.
do you have any?
Or a 20 entry or 32 entry, depending on what is the size to be considered and so on, right?
Yes. And any, let's say, performance or let's say anything in benchmark of a CPU designer that should be considered.
So for that matter, it's not just RRF. Entire computer architecture is basically it's a design space exploration. There is no unique answer, right? So, for example, why do you have to consider 64 KB of L1 cache? Why can't I consider 32 KB? Or why do I have to consider 32 rename registers? Why can't I consider 64 or something else and so on? So basically what happens is typically these processor companies, Intel, AMD and so on, right? So what they do is they first, when they want to design a processor, they'll identify targeted applications. Which applications for which I have to design this processor? Let us say I'm considering a general purpose processor. Now what type of typical scientific application or typical general purpose applications are a scientific applications which have large kernels and so on. They consider that, and now they run those things on architectural simulator with these parameters. Let us say I consider 64 KB L1 cache or 32 KB L1 cache, a set associative or a multi-level caches. All these things will consider in the architectural simulator and execute this set of benchmarks. Now we get the data for each of these. So typically they run thousands of simulations, different applications, different configurations and so on. And then you will have in the design space, you will get lots of design points. Now for each of the design points, you will have these values. And then based on that, they'll, of course, it's not necessary that only one design is going to satisfy all the applications and so on. So there may be some applications which get benefit from one particular design and some application may benefit from the other and so on. But the majority of the applications are benefited from some particular design. Maybe they'll freeze on that. And also at the same time, they'll also look at what is the budget allocated, right? For example, your number of transistors in a chip is, let us say, some 1 billion registers are there. Now you need to efficiently use this 1 billion registers or 1 billion transistors for all functionalities. And now again, the designer architect may say like, okay, I'll not give you not more than 10% of this entire space for you to come up with cache memories or memory hierarchy and so on, right? L1, L2 caches and so on. Now, as a designer, I have to intelligently use that space and so on. So given all these design constraints and so on, now we'll be looking at multiple options and finally we'll freeze on one particular thing. All these things happen at the architectural level only. That means architectural simulations they'll do. And once this is done, then once they freeze that, they take the design point and then go to the next level, RTL and so on. But till the time, they'll just keep on exploring. It's not, there's no thumb rule saying that, okay, this is the solution you have to use. And that is the reason why if you see, Intel microarchitecture is different from AMD microarchitecture. For example, in the cache hierarchy. So they will consider 3-level cache, L1, L2, private and L3 is shared. And maybe in one of the AMD architecture may consider L1 is private, but L2 is shared by 2 cores within a particular single multi-core system. Or so they can consider different type of inclusive caches, exclusive, non-inclusive, different type of designs and so on. All these are depending on what behavior they are getting with the scientific applications, and based on that, they'll just go ahead.
Okay. These are basically backed by the numerical metrics that we collect from microarchitectures.
Yeah. And that's the reason typically if you see any of the CPU side, we have this standard spec benchmarks are there. Spec.org, you can find lots of different type of benchmark suits. And typically we take those things and then we analyze executing those things on our design. And finally we'll see whether this is going to be beneficial and what is the area overhead, what is the energy overhead.
Thank you.
Thank you.